Welcome to AP Chemistry. History is dominated by slow movements of preparatory development, followed by points of punctuated exponential growth. Although we have limited time to discuss the history of chemistry, there is an enormous wealth to be gained from its philosophical exposition. Nevertheless, let us mark the most important milestones for atomic theory. John Dalton, in 1803, drew upon the ancient idea posited by Democritus that the substance of the world was formed of atoms. His theory stated that atoms are indivisible. Of course, this derives from the Greek word atemos, meaning not cuttable, and that these atoms, or of a given element, are identical, and that compounds are just simply combinations of different types of elements, i.e., atoms. He was right, Dalton, in reference to elements and compounds. However, we now know that atoms are not indivisible, but actually composed of subatomic particles, electrons, protons, neutrons. About 100 years later, J.J. Thomson discovered electrons inside of atoms. He subsequently produced a quote-unquote plum pudding model of the atom, in which the atom is composed of electrons scattered throughout a spherical cloud of positive electric charge. He was right in that electrons are components of the atom. However, there was absolutely no sense of a nucleus that was provided by later experimental observations. This leads us to Ernest Rutherford. In 1911, Rutherford and other graduate students fired positively charged alpha particles from a lead source at a thin sheet of gold foil. Most passed through with little deflection, but some deflected at large angles, with some even making their way back. This was only possible if the atom was first mostly empty space, but with positive electric charge concentrated in the center, as well as a concentration of mass in that selfsame center, which they called the nucleus. He was right in that he realized that the positive electric charge was concentrated in the center of the atom. However, he did not explain why the electrons still remained in orbit around that nucleus. Of course, the immediate analogy that came to mind was that of a solar system like model, a sort of Jimmy Neutron like vision of the atom. However, there is an important problem with this description. Earnshaw's theorem, a theorem important in relation to inverse square laws, states that there can be no points of static equilibrium in a field of force that is distributed according to an inverse square relationship. This would apply to electrostatic, magnetic, or gravitational fields, as well as to others. For example, there can be no single point at which an object could be stuck, both in its pull toward the Earth and toward the Moon. If it's gravitationally drawn to either the Earth or toward the Moon, it must be in free fall to one or the other. It cannot be in reference to both. So, what does that mean for us? It means that if we consider both the nucleus and the electron as point particles orbiting each other in space, a point of static equilibrium between them cannot occur. Either they are to be driven away from each other or driven towards each other. And since they have opposite charges, as the model provided below shows, the electron ought to immediately fall into the nucleus. Such a model of the atom is absolutely wrong. And the problems don't stop there. Recall that whenever an electric field is disturbed, an electromagnetic wave, light, is produced. Further, recall that to disturb an electric field, one must apply a force, for forces alone accelerate objects. Furthermore, a force is applied whenever an object accelerates, that is, changes velocity, either by speeding up, slowing down, or changing direction. In such a solar system view of the atom, the electron in orbit around the nucleus would constantly be changing its direction, which means it would constantly be undergoing a force, which means it would constantly be emitting light, which means that it would constantly be losing energy, till it would collide with the proton in the nucleus to form a neutron. Since matter is not emitting light all around us and randomly disintegrating all around us, this model of the atom is horribly wrong. Now, we could actually calculate how long matter would take to disintegrate according to such a model of the atom. 5 times 10 to the negative 11th seconds. Deeply problematic. Therefore, there is a key problem with our view of electrons. Electrons cannot be considered as functioning like point particles in space. But if we cannot treat them like particles, what can they be treated like? In 1913, Niels Bohr modified Rutherford's model of the atom by stating that electrons moved around in fixed orbits of size and energy. Electron energy in this model was quantized. We encountered this view in the previous video. And electrons could not occupy values of energy between the fixed energy levels. Now, this helped to explain the emission spectra that we had already discussed. However, it did not help to explain why the electrons wouldn't just emit energy and fall right into the nucleus. It took another scientist named de Broglie and Erwin Schrödinger in 1926 to state that electrons do not move in set paths around the nucleus, but they move according to wave functions. That is, it's impossible to know the exact location of the electrons. Instead, we have these clouds of probability, which we call orbitals, in which we are more likely to find an electron, whose regions of probability take the shape of waves. And this is still the most accurate view of the atom that we have to this day, being now supported by enormous experimental evidence. Now, to grasp the full implications of this, you must understand that a particle view of the world and a wave view of the world were considered to be contradictory to one another, as if stating that the world is made of bodies or particles or things and matter, versus the world is made of spirit or mind or ideas. The history of philosophy in reference to this scientific historical development is immensely useful. The solution to this seeming paradox was that bodies or particle like behavior arises out of the confluence of concentrated packets of energetic waves. It was as if one stated that our physical sense of the world arises out of the protuberance of energy in formation and in relation with each other. The key to making sense of this is to recall our understanding of light. Light was considered to be a wave, but then a particle view came to be integrated as well. If we take Einstein's full energy equation in the form of Pythagorean's theorem, we realize there are two components of energy by virtue of an object being at rest, which we used in the first unit, but also by virtue of an object's momentum, symbolized by the letter P, which is equivalent to mass times velocity. Light has no rest mass. That is, a photon has no mass per se. Yet light does have momentum. And the equation becomes E is equal to P times C. The implications of this equation is that light, which has no mass, can actually behave like it does, especially in high energy or high momentum situations. Furthermore, if we take the rest mass equation E is equal to mc squared and set it equal to the relationship from light, that E is equal to hc divided by lambda, that it is possible to get a function, a wave function, able to describe the wavelength of an object at a given velocity. This is called the de Broglie wavelength, and it illustrates how all particles can be treated as having wave-like behavior. The point here is that of perspective. To have a comprehensive view of the world, we must be able to integrate both perspectives, that of wave behavior and that of particle behavior, within the appropriate context. Let us take the following schematic. Waves are disturbances in a given field, but particles are specific positions within that field. In diagram A, wave behavior is dominant. In diagram D, particle behavior is dominant. Diagram A is least localized. So there's this large delta value or large uncertainty as to position. That is, we have very little certainty as to where the phenomenon actually is. But we have a low uncertainty as to its momentum. That is, we have much more certainty as to its component energy. However, diagram D is most localized. So there is a small delta value or small uncertainty as to its position. That is, we have a high certainty as to where the phenomenon is. But we also have a high degree of uncertainty as to its momentum. That is, we have little certainty as to what its actual component energy is. The takeaway is that one cannot know both perspectives at exactly the same time. The only way to see electrons, or anything for that matter, is to smack the object with light. However, if we use high energy light, the light will so alter the electron distinctly that we will have low uncertainty as to its position. We will know exactly where it is. However, we will have so significantly altered the original state of the electron so that we will know very little about its actual energy. If we, however, use low energy light, the light will hit the electron indistinctly, such that we will have a high uncertainty as to its position, but the original energy state would no longer be as altered, and thereby providing us with a greater certainty as to its energy. We cannot, however, know both the position and its momentum simultaneously. This then is the basis for Niels Bohr's indeterminacy principle and the basis of complementarity within the world. With this in mind, let us return to our view of the atom, ready to treat the electron like quantum mechanical waves. Recall that the principal quantum number, n, in reference to the electron, actually refers to its number of nodes. Following the work by de Broglie on the mathematical equations for the behavior of waves, Schrödinger and Heisenberg mathematically determined regions where electrons would most likely be found in the form of wave functions. We must keep in mind that the wave function that we are looking at is a radial probability distribution map. That is, it indicates the probability of finding an electron. However, it takes the form of a three-dimensional wave. Provided we see first, second, and third energy level s orbitals, 1s, 2s, 3s. One can easily see that s here refers to spherical, and the energy level referencing the number of nodes. Within the second energy level, we not only have the possibility of 2s, but also another sublevel, 2p. And since these orbitals are farther from the nucleus, we're able to integrate more of these orbitals. Therefore, we have 2p in the x-axis, 2p in the y-axis, and 2p in the z-axis. Note that as we compare 2p to 3p to 4p in the next slide, all that will change is the number of nodes within that sublevel. The greater the energy that an electron has, the greater the number of nodes. The D sublevel, now possible in the third energy level, has even greater number of orbitals, 5, within the same region. Again, note how 4D compares to 3D, with increased energy and increased number of nodes. Our simulation ends with 4F. Although there are theoretically more sublevels possible, For our practical purposes, we will only encounter S, P, D, and F sublevels. Thus, we have four possible quantum mechanical numbers. The first refers to the energy level, or distance from the nucleus, as well as the number of energetic nodes possible. The second refers to the electron's shape, that is, S being spherical, P being propeller shaped, D donut shaped, that's really referring to the central orbital there, and F for flower. The third quantum mechanical number refers to the possible orientations in space. With more orientations, the more energy and more elaborate shapes that are possible. The fourth quantum mechanical number will be discussed shortly. The order of electron configurations and notation is due to the differing energy between sublevels, as shown by the schematic. We will discuss this more in depth in the next unit. The most efficient and useful way to do electron configurations is to use the periodic table. If I wanted to write out the electron configuration for bromine, I would begin with hydrogen and fill each electron accordingly. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Again, the ease is by using the periodic table, noting that the first two columns are the s block, and that s orbitals can only have 2 electrons within their orbital. Again, noting the p block, which has 6 columns, and that since there are 3 orbitals in every p sublevel, that this corresponds to the maximum number of electrons that can fill a p sublevel. Again, for the D block, where the transition metals are located, all D block elements can have 5 D orbitals, a maximum of 10 electrons, which corresponds to their number of columns. Finally, in the inner transition metal group, the F block, there are a total of 14 columns, which correspond to the 14 electrons that can fill 7 F orbitals. The final quantum number, the fourth, refers to the electron's spin within a given orbital. Only 2 electrons can stably exist within an orbital. Due to their similar electric charge, they naturally repel. However, if oriented opposite each other, their magnetic poles will also attract, and there is able to exist a stable conformation with each other. This then is the basis for stable covalent bonding, when electrons in singly filled orbitals overlap to complete each other's attraction. The essential takeaways for this video are as follows. Electrons exist as both particles and waves. Waves when bound to the nucleus, and particles when unbound to the nucleus. The plot of electrons, which is what we call electron configurations, tell us where the electrons are in reference to the nucleus. There are 4 aspects to this. The first, energy levels, dictating the distance from the nucleus. The second, sublevels, which dictate the shape of orbitals around the nucleus. The third, sublevels having a number of possible orientations corresponding to their orbitals that are in that sublevel. Finally, orbitals can only hold a maximum of 2 electrons with opposite spins.
Till next time when we consider the mysteries of the absolute,